All right, welcome back. We are moving on to the third lesson in Unit 7, though it's 7.4, but we are going to be looking at logarithm and the logarithmic functions today. Before we start, we are going to actually do a quick review of the inverse function and what that means, okay? So the inverse function of y equals to f of x is if you recall, inverse really just means we switch x and y, but we don't write it as x equals to f of y. We write it as y equals f inverse of x, right? That's the inverse function. We write as y equals f inverse of x. What characteristics exist between the domain and range of f of x and f inverse of x? Recall the domain from the f of x becomes the range of the inverse of function, and the range of f of x becomes the domain of the f inverse of x. Okay, so that's what's happening, right? Because we're switching x and y, so domain becomes range and range becomes domain. That makes perfect sense. Okay, so now we're going to take this fact and we're going to draw the inverse function of the exponential function right here, 2 to the power of x. Okay, so now I'm going to split. Okay, I'll do f of x over here, and I'm going to make a table of values. Recall, we always use the three x values. They are -1, 0, and 1. 2 to the power of -1 is 1/2, 2 to the 0 is 1, and 2 to the power of 1 is 2. And we are going to have some asymptotes. Recall, for the exponential function, we have a horizontal asymptote, and it is y equals 0. And we're going to have the domain being all real numbers, and range being y is greater than 0. Okay, so that's the domain and range. So now I'm going to plot these points and graph this function right here. -1 and 1/2 is here. 0, 1, 1 and 2. We have horizontal asymptote right here. And here is my graph. Oops. Something like this. Okay, so there is my exponential function. This is the exponential growth. Okay, with the base 2. Okay, so now we're going to take this table of values and we're going to draw the inverse function. Okay, so really all we needed to do is then take the original table of values and then just switch x and y. So now my x values would be 1/2, 1 and 2. Y values be -1, 0, and 1. Now we do not have horizontal asymptote anymore. Instead, we are going to end up with a vertical asymptote because horizontal becomes vertical, right? X becomes y, and therefore horizontal asymptote becomes vertical asymptote with the equation x equal to 0. Again, y becomes x. Domain was the range. Range was the domain, right? So you can see we just switched these two. Okay, so now I'm going to plot the points. 1/2 and -1. Sorry, that's not the right place. 1/2 and -1 is here. 1, 0, 2, and 1 is right here. So here, oh, and then we have vertical asymptote. So here's the graph. Okay, notice that really these two graphs are just a reflection over the line y equals to x. Okay, because that's what inverse function does on the graph. Okay, so ladies and gentlemen, this really is the inverse of the exponential function, which we call this log x. Okay, so this, if you write it in the more of a conventional form, it's y equals log base 2 of x. Okay, this has this table of value. If you want to draw this, this would be the table of value. That's log base 2 of x. The base 2 came from right here. That's base 2. Okay, so the key takeaway here is that the exponential function, the log function, they are simply inverse of each other. Okay, they are just simply inverse of each other. We have a special name for it, right? For example, sine function has an inverse. We call it sine inverse of x. There isn't really a special name for it. I mean, some people call it arcsine, but nothing really. Not like a special name, right? But log is a special name for the inverse function of exponential functions. We call it log. Okay, so that's what log is. Okay, so the term logarithm is used to describe the inverse of a power. For example, the inverse of 10 to the power of x is the logarithm to the base 10 of x, which is written as log base 10 of x. Okay, now if it's base 10, okay, we don't actually write base 10 because we use base 10 too much and we are just lazy, so we don't want to write base 10 all the time. So if it's base 10, we don't write the 10 there. However, you can see the example that we just did here. The base was not a 10. It was not a 10, so we have to write it. Okay, so it's a base 2 in that case. This case is base 10, but we don't need to write it. Okay, we read this as log. Again, if it was not a base 10, you need to say log base of something. I'm going to say base 10 here of x. Again, if it's base 10, you would just say this as log x. But if it's base 10, if it's base 2, then you read this as log base 2 of x, log base 20 of x, and so on. But if it's base 10, you just say log x. Okay, so a little bit shorter if it's base 10. Okay, so here's the definition of a logarithm. You can read this, but I find this kind of confusing. Really, what the key takeaway here is this right here. If, I don't know why it says when, but if log base b of c is equal to a, in that case, that means c is equal to b to the power of a. So what I'm saying is these two are equivalent. Okay, this is equivalent to this. This means that, and that means that. Okay, they're just the same thing, but written in a different form. One is the log form, and one is the exponential form, power. So notice how base is the same, right? That's base b. This is also base b. Because they're inverse of each other, notice how the answer for the log a is not the answer for exponential form. It's the number we're raising the power to. The answer for the power, c right here, is not, again, not the answer for the log. It's the number that we're taking the log of, right? So you see how they just switch positions, right? This was the answer, but in the exponential form, that's not the answer. This is the answer for exponential form, but it's not the answer for log. You just swap them. But the base remains the same, right? This is base b. This is also base b. Okay, so that's the key takeaway. They are equal to each other. Okay, they are equivalent, just written in a different form. Okay, but be careful though. Okay, log and exponential power, they are not equivalent. They are inverse of one another. Okay, they are inverse of one another. However, these two are equivalent. Okay, so here are some conditions that it needs to meet. Okay, b has to be bigger than 0. Makes sense, because if the base is not bigger than 0, then you're alternating between positive and negatives. B cannot equal to 1, because 1 to any power is 1. That's not really exponential anymore. C has to be bigger than 0, because if the base is bigger than 0, and that positive number raised to any power is going to be bigger than 0 as well, right? So that's why C has to be bigger than 0. So that's key here, because that means when we take log, you cannot take log of a negative number. Okay, so that's the important right there. Okay, so keep that in mind. Okay, so we're going to do some practice. We are going to switch the forms back and forth. Okay, so here's some practice questions. I will show you this one, and I'll let you do the rest. Here, part A, this is the exponential form. We're going to turn this into log form. So again, it's going to be log. Base is not going to change. The base here is 3, so it's going to be base 3. That's not going to change. And here's a number, and this equals to a number. Okay. Now keep in mind the answer for the exponential form is 27. That's not going to be the answer anymore for the log. It's going to be the number we take the log of, and the power, the exponent, becomes the answer for the log form. Okay. Notice how the 3 and 27 just swap positions. Okay, this is the log form. We're going to change this into exponential form. So for log, there are these 3 spots that you need to fill in, okay, the numbers. For exponential form, same thing, you have 3 spots. Okay, the base will never change, so 6 is the base. Okay, this was the answer for the log form. It's not going to be the answer for the exponential form. It's going to be the exponent. And this was the number we're taking the log of, so that becomes the answer for the power form. Okay, so I'll let you do the other 4 and see if you can write them in the different form. Okay, so exponential form, change it into log to exponential. Okay, I'll let you try that. Good luck. Okay, so hopefully these are the results that you got. Again, it's just basic practice of changing the forms. It's quite important because you'll know in the next part, we're gonna switch forms to actually evaluate, okay? Because we're still not quite used to logs. So I think if we can change it to power form, it's easier for us to grasp the idea and be able to evaluate. Okay, so let's take a look here. We want to evaluate these logarithms. Okay, so this might be difficult to think about. Okay, well, what's log base 2 of 8 is going to be? Okay, so what we're going to do is we're going to change this into exponential form. Okay, so I'm going to say log base 2 of 8 is equal to x because I don't know what it is equal to. Now I'm going to change this log form into exponential form. So this becomes 2 to the power of x equals to 8. Well, now I know how to do this. 2 to the power of 3 is 8. Now, if you don't remember how to do this, recall we need to change to the same base. So 8 can be written as 2 to the power of 3. So you can see clearly x equal to 3, and therefore this equal to 3. Okay. Similarly, for part B, we're going to say this equals to x. And I'm going to say this then means 4 to the power of x is equal to 1 over 32. This is just some exponential function that we can solve by turning both sides into the same base. I need to change both sides to base 2. 4 is same thing as 2 squared. 1 over 32 is same thing as 1 over 2 to the power of 5. That means this is 2 to the power of 2x. This can be written as 2 to the power of negative 5. Remember, this is in the denominator. We can move to the numerator by making the exponent negative of what it was there. So this means 2x equals negative 5, and x is negative 5 over 2, right? Dividing both sides by 2. Again, once the base are the same, then you can say that, well, as long as the exponents are the same, then they would have to equal to one another. Okay, finally, the last one here. Again, I'm going to say this is equal to x. That means 2 to the power of x is equal to the cube root of 4. I need to rewrite this as a base 2 once again. So this is going to be 4 is same thing as 2 squared. Now we can rewrite this as 2 to remember, you can turn a radical into exponential form. This is going to be 2 to the power of 2 over 3. And clearly that means x has to equal to 2 over 3. Okay, so I kind of did that in no time. Hopefully you understood what I was trying to show you. Try it. There are 3 questions down here. Give it a try. If this was too quick, maybe you can watch it again. Okay, good luck. Alright, so I hope you got these 2 answers as your result for part A and part C. I left part B here because that one is a little bit different than the ones I show you. So I'm going to do this one with you. But hopefully you got 3 and negative 7 over 2 for A and C. Okay, part B, this is not in the log form. This is in the power form. So guess what we're going to do? We're going to turn this into exponential form. We're going to turn this into log form. Okay, so because this right now is in the power form. So I'm going to say 5 to the power of log base 5 of 25 is equal to x. Okay, now this is, again, you can see this is 5 to some power equal to x. This is power, so we're going to turn this into log form. Well, we can do that by taking log of base 5. Again, the base will never change. Okay, this was base 5, so this is still going to be base 5. The answer was x, so now this is the number we can take the log of, and this would then equal to log. This is going to be the exponent, all right? So this is log base 5 of 25. Okay, we're pretty much done. I mean, it says log base 5 of x is equal to log base 5 of 25. That means, again, they have the same base, and we're taking the log on both sides. That means as long as x is 25, then it's the same, right? If you switch x with 25, then they are exactly the same thing. Okay, so x is 25. You finished. So here, notice how we have the same base, 5, as in the power form, and the 5 as the base for the exponent for the log. As long as they're the same, it's going to be this as the answer. So what I'm saying is this. If you have 4 to the power of log base 4 of 10, this is going to equal to 10 because that's the base 4. That's also base 4. Okay, so that's kind of a rule you can kind of remember if you would like. If you don't, you can always figure this out quite easily by just simply convert this into a log form. Okay, I guess in the other case you might ask then, well, if in the power form and if you have the same base for both the base and the exponent, you get the answer for that. Does that mean if I have log base 4 and this is 4 to the power of, let's say, 5, since that's base 4, that's also base 4 for the power form, does that mean this equal to 5? Is it true? The answer is yes. Okay, it's actually true. We'll talk more about this later on. But yes, this is true. This is definitely true. You can see base 4, also base 4 for the exponent, right, for the power. All right, that's all we're going to talk about for now. We are going to move on, and we're going to figure out a graph of the log functions a little bit here. Okay, so here it says graph f of x equals to log base 3 of x using a table of values. So remember this, I can write this as log y equals log base 3 of x. Remember, this is the inverse of the exponential form of the power. 3 to the power of x equals to y. So what I'm going to do is this. In order to draw this, okay, I'm going to still use the table of value, of course. But what I need to do is I need to think, when I see this, I need to think about this. 3 to the power of y is equal to x. Because these two are equivalent, right? These two are equivalent. But this, we don't do this very often. We usually write it as y equals 3 to the x. But these two are simply inverse of one another. So what you do is you think about this, but then you write like that. Okay, I don't know if you understand what I'm saying here. Think about this. For example, if I want to draw this, I first put down my x values, -1, 0, and 1. Right? I would do this. But because we need to think about this, okay, we think it that way. So what we do is, okay, we take a look at this, but we put it under y column. Okay, because ultimately that's what we're doing. Okay, because these two are equivalent. Remember, these two are equivalent, and these two are inverse. Right? So I think about this function, but instead of put it into the x, I put it into y. And now I can go 3 to the power of -1 is 1/3, 3 to the power of 0 is 1, 3 to the power of 1 is 3. And that's how I come up with my table of values. Okay, so basically we use the power function, right, the exponential function. We take that table of values and just switch x and y. Okay, and I know this is going to be base 3 because, right, you can see that's the base 3. So I know it's going to be base 3, so that's why it's these three numbers right here. Okay, so now we can actually graph. 1/3 and -1 is right here. 0, 1, or 1, 0, and 3 and 1 right here. We should have vertical asymptote, as you can see from the first page, right? For log, we don't have horizontal asymptote, we have vertical asymptote. And here is the graph. Okay, so I think, as you could probably imagine, we're going to transform log functions pretty soon. Okay, not today, but pretty soon. Okay, so that's table values. Part B, find the intercepts. You can see we have an x-intercept. It is at 1. Okay, it's always at 1 unless we transform the function. Okay, it's always at 1 for a base log function. Just like when we have a basic exponential function, we always have y-intercept of 1. But for log, we always have x-intercept at 1. Asymptotes, again, we have vertical asymptote instead, and this is going to be x equal to 0. Sorry, yeah, that's right, x equal to 0. Domain, we do have restrictions now, right? X has to be bigger than 0, but range, y can be any value that we want it to be. Okay, y is the element of all real numbers. Okay, so that's the basic log graph. Okay, it looks like this. We're going to transform this shortly. Okay, so here's the definition of logarithmic functions. The log function f of x is equal to log base b of x. Again, b has to be bigger than 0. We talk about this, and b cannot equal to 1. We talk about this, and x has to be greater than 0. Right? You can see the domain is that x is greater than 0. So everything we talk about really, and this is the inverse function of f of x is equal to b to the power of x. Okay, that's just the inverse function of that. Okay, and think in the above definition, why does b cannot equal to 1? I think we talked about this. If the base is 1, I mean, if we convert into the exponential form, I mean, 1 to any power is 1. That's not really exponential anymore, right? So b has to be greater than 0 and not 1. Okay, so here's the challenge for you. You can try this one. It's kind of tricky, okay? We are drawing y equals to, okay, you know what? We can do this, not a problem. And let's see what you notice, okay? Actually, you know what? I'm going to ask you to try it and see what you get. Okay, so we're gonna, so that one is it, and then this one I'll do over here. Okay, so this one really, again, what you need to think about is this. I need to think about root 2 of to the power of x is equal to y. But then again, when you think about these x values, you put it under y column. And remember, you always put -1, 0, and 1. Okay, so root 2 to the power of -1 is 1 over root 2. Okay, root 2 to the power of 0 is 1. Anything to the power of 0 is 1. And root 2 to the power of 1 is root 2. Okay, not very exciting. Similarly, we can do it over here. This one, you need to think about 2 to the power of x is y. So again, think about the x value you're gonna use, but put it under the y column. -1, 0, and 1. That's 1/2. That's 1, and that's 2. Okay, and now we can graph. Okay, 1 over root 2. I can't remember what that is. I think that's 0.7 or something like that. Root 2. That's 0.7. That's right. So 0.7 and -1. 0.7 and -1 somewhere here. 1 comma 0. Root 2 is 1 point something. Can't remember. 1.7? 1.4, sorry. 1.4 and 1 is right here. There's the graph. Okay, now for this graph, 1/2 and -1. 1, 0. 2 and 1. Same vertical asymptote. And there's the graph. Hopefully that's all you got. Okay. Now it says, what do you notice about these two functions? Have you noticed anything? Okay, I'll let you think about it. Okay, so I don't know if you noticed this. Okay, so I have to apologize. This was kind of misleading, but I'll turn this into, if you convert this into, if you convert this into the power form, this really becomes root 2 to the power of y is equal to x. And in this case, the second one here, this is 2 to the power of y equals to x. Now, the graph, you might not be able to see it, but let me show you this. We can rewrite root 2 as 2 to the power of 1/2. And this is to the power of y equals to x. So really, this is 2 to the power of 1/2 y equals x. So if you compare these two, what happened was, this was y, this is 1/2 y. Do you remember what happened in that case? We did this in unit 3. Or sorry, unit 4. 4? 3? I can't remember. 4, I think. When we replace y with 1/2 y, remember this means that there is a vertical expansion by a factor of 2. Okay, this is being vertically stretched. Okay, so this graph is actually vertically stretched from this graph by a factor of 2. Okay, because we replace y with 1/2 y. Okay, so anytime you replace y with 1/2 y, it's being vertically expanded. Okay, so and I think you might be thinking, well, I thought it's half, right? Be careful, it was this, right? A f of x. Let's just talk about a, because a is the one that's changing vertically. But if you move a to the left, if you change this into this, right, then you see that we're changing y to y over a. In that case, you can see this is 1/2. 1/2 y is the same thing as y over 2. If we move that 2 to the right hand side, it becomes 2f of x. So it's actually vertically expanded by a factor of 2. Again, you might not be able to see it from this. Actually, you probably could. Notice how though it's a freehand drawing, notice how this is flatter than that one, right? That one kind of is higher. So this is actually going up faster. I think you can see from these 3 points, it's more wide. It's not as narrow together. Whereas this, you can see this clearly is going up faster. Okay, so this one is actually vertically expanded by a factor of 2. Okay, again, you could notice that, but it might be difficult from the graph. But that's really what happened here, and that's how these two graphs are related. Anyways, that's just the challenge. That's just on the side. Okay, so we will do more transformation later on in the unit. Okay, so let me know if you need some help. Otherwise, good luck with your questions. See ya.